In a physics experiment, a 1.3 kg dynamics cart is placed on a ramp inclined at 25 degrees to the horizontal. The cart is initially at rest, but is then pulled up the ramp with a force sensor. The force sensor exerts a force on the cart parallel to the ramp. Negligible friction acts on the cart. A. What force is required to pull the cart up the ramp at a constant velocity? And B. What force is required to pull the cart up the ramp at an acceleration of 2.2 meters per second squared? Starting with A, we list our givens. We know our mass is 1.3 kilograms, our angle theta is 25 degrees, the gravitational field strength of the Earth is 9.81 newtons per kilogram, and we also know that the net force of everything in the system is 0 newtons, since the cart is moving at a constant velocity. Now, we draw our FBD and assign up the ramp as a direction that is positive. We know that the sum of all forces acting parallel to the ramp is equal to 0 newtons, and is made up of only the applied force and the parallel component of gravity. We know that the sum of all parallel forces is 0, and Fg parallel to the ramp is equivalent to mg sine theta. Then, we can sum in all our values, and find out that the applied force is roughly 5.4 newtons up the ramp. When summing in your values, don't forget that the Fg component is actually negative, since it's acting down the ramp. You end up taking the negative of a negative, which results in a positive value for Fa. We have now solved part A. For part B, we list our givens and draw our FBD again. Our only new given here is that our acceleration is 2.2 meters per second squared up the ramp. Using this, we can solve for the net force acting on the system. Since we know Fnet equals ma, we can simply sub in our mass and our acceleration and find out that the net force is 2.86 newtons. Once again, we know that the net force of the system is equivalent to the applied force plus the parallel component of gravity. Recall that the parallel component of gravity is mg sine theta, and that we have already solved for the net force. Using this, we can rearrange the equation to solve for the applied force. Taking into account two significant digits, the applied force turns out to be 8.2 newtons up the ramp. We have now solved part B.